Our next speaker is a U.S. Navy second-class nuclear machinist's mate veteran. After completing the Nuclear Power Engineering program and obtaining her professional license, she spent 10 years maintaining nuclear mechanical operations on A2W, A4W, S1G, and modified S7G class reactor plant systems. While currently pursuing an accelerated master's degree in Renewable Energy Engineering here at OIT Wilsonville, she has worked for the Bonneville Power Administration in the Transmission Line Design Department and Control Operations with a focus in electrical effects and transmission efficiency. Here to discuss the mitigation of transmission power line losses through transposition and the associated economics, please welcome Autumn Engh.
So when I first started getting into energy and nuclear and even coming here and thinking about renewable energy, there was a lot of emphasis on generation, on how we're making the Sparky Sparky. But the problem is that nobody really talks about how the Sparky Sparky gets from the Sparky Sparky places to the people places. And that's what BPA does. They do transmission of electrical power from the Sparky Sparky places to the us places. So once I started thinking about how it gets there, I realized that in America, this is something we don't super have to think about. Right now, our electrical grid system is meeting demand without too much problems. We have electrical power outages every once in a while. They don't last for months. They last for a couple of hours, sometimes a day. Generally, in America, we're looking at about 20% electrical line losses total. And that's our worst case scenario. And basically, 100% of people have access to electricity in this country. When you're looking globally, it's a totally different picture. Around the world, those electrical losses that don't really impact our access to electricity at all are about 80%. So 20%, 80%, there's a lot of stuff going on over there when it comes to electrical side. And 1 in 6 globally don't have access to electricity at all. So while the rest of the world is all good and important, I'm going to shrink this down to just to talk about Portland's electrical grid so that it makes sense on kind of a local level. Sound good? All right. So Portland's electrical grid effectively is a bucket with holes in it. If we were to assume that all of our transmission lines were like the light rail, and passengers get on at one side and get off at the other where we can use them, some people are jumping off the train when they shouldn't be jumping off the train. We can be losing up to 20% of the electricity generated before it even gets here to the people places. This is my power line. So from one end, we have our electricity generated. It goes through all the power lines, and by the time it gets to the other end, we are down up to 20%. And that's just from induction field losses, from the magnetic fields interacting with each other. This is going to take a while. 50,000 homes worth of power is lost just in transportation. That is, in fact, the next 20 years of estimated Portland electrical growth, or electrical demand growth, I should say. So the next 20 years of growth is being lost somewhere between us and where the Sparky Sparky is made. Which basically means that in order to get 100% of the people in the Portland area power, we have to make more than 100% of the power. We have to automatically assume that we're going to get these losses and generate a ton at the other end in order to get over here, which is kind of like working for free. Now, we've known about this for a pretty long time, that these losses exist. But historically, when the electrical grid was being put together and as the industry was being built, we didn't care a whole lot about efficiency, about electrical losses. Frankly, gas and oil were going to last forever. There was always going to be coal. Everything was going to be awesome. There was no need. Who cares if we're only getting 80% efficiency? As long as we can have our toasters and our microwave ovens and charge our Teslas, we're good. Now we're realizing that's not so much the thing. Luckily, we have science. We have the magic of transposition to fix this. And this is our transposition fairy, who is not a copywriting figure. Actually, I should probably explain a little bit. Okay, so what happens in electrical lines is that each one of these lines going through in a different phase has a field that forms around it. And that's just a material property. Physics is physics. Until we figure out how to beam electricity through the air, we're going to have to send it through wires. And wires have internal things that siphon off our electricity. They have passengers on the train that just sit there and do nothing. They take up space. We can't use that space for anything else, but we don't get any work out of that space when we get to the far end. They're like teenagers. They don't do anything. So each one of these lines has an electric field. No, I didn't play with the stylus. Has an electric field that's around it, that it's generating, and a magnetic field. And as those interact with each other, they basically induce current and voltage into it. You end up with inductive and capacitive losses of the line. Now, some of those we can't do anything about. We're never going to be able to do anything about until we figure out what Tesla was talking about with beaming electricity through air. But for right now, we have these losses, and we do have some way to deal with it, and that's transposition. The problem is that it's kind of a pain in the butt, is effectively. Oh, that looks really good. Currently, when you talk about different policies, different utilities, EPA, different government entities, there is no one transposition standard. The science is there. The science has been there for 60 years, that this is a good thing, that this would mathematically work. But when exactly to do it? You don't want to do it every single one. It's like 5 times as expensive as a regular power line. A regular power line, you're looking at a rule of thumb of about $1 million a mile. And that can go up to $5 to $7 million a mile if you're using transposition. Most beam counters see that and just go, no, we are not doing that. We are not going to have 5 times the budget. So right now, when to do it, when it makes sense to do it, is before 25 miles, they're pretty sure you don't need it. Over 300, you definitely need it. And anywhere in the middle, you should ask an engineer and they should tell you. So there are literally engineers with the giant budget that engineers have, the giant cost that engineers cost their company, sitting there doing mathematical calculations for every single project to see if you should use transposition and would. So this is what we do right now. You go through, you do all the math, you calculate your electrical losses. Once you get, this is how much electrical losses I'm getting from something I can do something about, then you jump on the other side. And you go, okay, well, how much is transposition going to cost? So you figure out, this is all the money I'm losing from the electricity that I could sell. And on this other side, this is all of the cost that's associated with using transposition. And you pick someplace in the middle. This can take several days. It took me as an intern a couple of weeks. But when you do it regularly, it can take a couple of days to look at all of the information and analyze exactly that configuration pattern for exactly that transmission line. Because each one's individual, they are all snowflakes. So you have to do all of these calculations every single time. I think, at this point, with this technology and this can-do attitude, that we should just have a computer program where we push a button and it does it for us. That's my assumption. Physics is physics, material properties are material properties, and all of that is database data. We should have something that will grab the information that we need and do an optimization for us. Yes?
What do you do to the power lines that's considered transposition?
I'm glad you asked. I'm totally going to go over there. Okay, so we talked a little bit about all of the different things that are going to happen. When you're getting into the profit side, you have to calculate what are the new builds that we're doing, what are all of the money stuff, basically. So one side of this is going to be all of the profits that you're losing, all of the losses that you're going to have, all of the infrastructure upgrades, everything that you have to do over here, and all the money that you're losing through these losses that you're getting in your electrical line. So all this siphoning off of real power. And over here, you're going to have all the transposition costs. All the additional time, all the additional engineering that goes into it, the civil engineering, the building time, maintenance schedule, all that jazz. And you have to take all of the money over a 40-year period, because these lines are supposed to last at least that long. So you're saying, okay, how much is it going to cost to do transposition? And is that, I'm going to say this word, amortized? I'm not. Amortized. Okay, perfect. Thank you so much. Over that 40-year period. If the construction costs are way more than what you could sell that electricity for, then you don't do it. But what if those are way less? What if all of the costs of construction are less than all of the money that you could make selling that electricity? Well, then you do it. That's something that we should be able to program as an easy algorithm, as an easy software. Yes?
Do you do like a present cost basis, all the costs to evaluate that?
Well, you have to evaluate both of them over the 40-year period. So how much electricity are you going to lose over 40 years? How much is that potential profit versus how much, because the construction cost you're paying now. So basically what you want to get is that amount of time it's going to take to break. And it can be higher, it can be lower. You can say, okay, well, we'll make our money back in 10 years. We'll make it back in 20 years. Yes?
What about cost avoidance of additional generation that you wouldn't have to do in the future because your lines are more efficient?
Yes, that is an important point as well, and that is also being included. So his question was about, what about avoidance costs? Now, because we're using this 20%, this is like kicking all the deadbeats off the train. We now have seats for real power that we can use. We're filling that train up and taking it from point A to point B. So because of that, we don't have to build a new line out to the dells. Anybody who's ever driven out 84, there is not a lot of space out there to add more transmission lines. If we can put off putting in a new line and just use the lines that are out there, we've got at least the next 15 years of energy demand growth for Portland taken care of without doing anything else. Yeah?
Has anyone done the math as far as if, with all new construction, to make solar panels mandatory to be able to help reduce the electrical footprint versus having the cost to be able to do this type of technology?
Right now, that's a little premature. What I'm thinking is, don't get me wrong, I love me some solar panels. I love me some wind turbines. I'm all about that stuff. But right now, we just got a requirement to start being more renewable. That's not really being implemented yet. Even if that stuff gets approved tomorrow, we're still looking at a time frame before that could be built, before plans, before farms can be put in, before all that stuff can get tied in. So this is something that can happen right now, before PV becomes cheap, before wind turbines become more optimized, before we figure out how to deal with the energy storage problem. This is something we can do to decrease our energy usage right now without having to wait for that technology to catch up. And then when it does, we've got full and open coal roads. We don't have anybody who's just hanging out in the lane taking up space. Does that make sense?
Yeah, I was mainly thinking like Southern Hillsborough, the 10,000 homes that are going to go in by 2020 in that area, and having the builders a standard to make all of those solar-based homes to be able to help deal with the situation from an energy.
Well, here's the thing, is those are all Sparky units. They're all generation. So if those homes make extra generation that other people want to use, they still have to get there. And so this is like putting in another ramp on the freeway without having to expand it side to side. This is a free lane. Okay, so safety first. We have to turn off our power lines before we do anything with them. It's important. So what transposition is if this is A phase, this is B phase, and this is C phase of the three different phases of three-phase AC power. Can you guys see this?
Yeah.
Okay, so what happens is between two towers, you physically alter the wires so that your phases are in a different configuration at this side. So the problem is you have to keep these far apart, because if these get too close together, you're going to arc across and there's going to be sparks in the people's faces and it's going to be bad. Like, way bad. So what you do is you have a special tower over here that spreads the lines out and starts to do a geometric shift. By the time you get to this other tower, the shift is changed completely. So now your A phase that started over here is now over here. Your B phase is now over there. That started down here is now over there. And your C phase is now in a different position. Yes?
Why do you shift them?
Okay, so the reason we're physically shifting them is that it's like separating two noisy kids in a classroom. Okay, over at this end where the lines are right next to each other, their magnetic fields are talking at the same places. All the places where they have an amplitude, a spike in their magnetic field that's really high, are all in the exact same place. So as you go distance, remember this is just between two towers, but this could be hundreds of miles long. And as you go on, these lines have gotten really used to sitting next to that person. They're talking more and more, the coupling effect is happening a lot stronger, so your losses are getting higher and higher. So why you physically change them is it's like separating the noisy kids in the class. They're now with new people, they're not going to start talking right away. So basically you're breaking that attraction between the lines so that the losses are no longer occurring at that really high level. They have to start over. So the thing is where to do this. If we've got a 3,000-mile line down to California, where are we going to put these? We don't want to put them too short. That's going to cost way more money. Yes?
Where does the 5x cost come from?
It's from these towers. So because you're having to expand outward and rotate them, these towers have to be specially designed. Each tower is a snowflake, but these ones are especially robust. You have to have a very, very strong base, and you have to do all of your normal safety calculations so that wind and stuff doesn't hit your transmission lines. You have to do more of. Because you are physically locating them in three-dimensional space, you have to make very sure that nothing is going to get these close together. Remember, these lines could be 500 kilovolts. We're talking about 500,000 volts on each one of these lines. So it doesn't take a whole lot for them to arc and spark and bad in the people places. Does that make sense? The cost is basically that this tower needs to be specially engineered. All of the clearances for lining it take longer, so there's more manpower that's involved. So you've got engineering, you've got more material costs, you've got more maintenance costs that are required with it because a transposition tower requires more safety checks. And you've got the increased manpower for putting it in. So it ends up being about 5 times as much. Yes?
And you would do this twisting of wires periodically in a run, or?
Well, that's the thing, is you have an engineer who sits down and spends days calculating where would be the best places to put this. So what I'm doing for my thesis project is I'm coming up with an optimization software. So because it's physics, every line that you use, no matter how you configure it, each one of these is a known factor. It's not like people just go to Home Depot and they pick a wire off the shelf. There are only certain ones that they use, and all those material properties are already been tested and already documented. So what I did is I set up a software where I could run a non-transposed line and check what the losses were on it for all of these different materials. And I came up with a library database of that. Then I transposed the line and I ran the simulation again. And I got what are the losses that we could get both in the low range and in the high range. What could I capture back by using transposition? And all that data is pretty standard. If you have a 100-mile line that's made of 2.5-inch expanded steel line that's 30 feet off the ground, you can calculate what those losses are. And you can calculate what portion of those losses can be fixed by transposition. And all of that is just a giant Excel data sheet. So the software that I'm developing, or that I should say I developed, takes all of that data, you put in, this is what it's made of, this is how long it is, this is the bundling I have, this is the power it's at, and it will tell you My optimum is every 65 miles, do a transposition, or you're losing money. Every 50 miles, every 85 miles, you need to do a transposition. So this is not every tower. It's just every so often you need to do them. And currently, that's a gut check. So there is some guy who's been working in the field for 40 years and knows this stuff with a Yoda level of knowledge that I could never hope to meet. And he looks at it and goes, that's 70 miles. And everybody knows, Alan knows this stuff, and he said 70. But is that the most optimum place? So just in my analysis of the stuff through 84, with the SCADA data from Bonneville, at least 5% of the transpositions that are done out there are not done at the most optimum point. We are losing power by where they're currently located. Yes?
This is a great idea. Have you protected your idea with the patent or something? I mean, this is a very practical, very profitable concept.
Theoretically, it could be. I did the Clean Tech Challenge last summer. It turns out that I am not a business person. And so what I've decided to do is I already have a deal with the federal government. They're buying my algorithm. And then, honestly, I'm open sourcing it.
Wow.
So that organizations like Engineers Without Borders, back to that 80%, if you have an engineer who has 2 weeks in a foreign country to build electrical lines, they could use every efficiency method that they could get.
That's very generous of you.
Okay, so we have our transposed line and we are powering it up. It doesn't get fully 100%. But if we can even capture 5% based on where the transpositions exist now and are not in the most optimum location, it is a lot of power. So most conservative estimate is that we can capture about 5% of the losses through optimum placement of these transposition towers. And that is going to take a while. Is 18,000 homes in the Portland area. So this could save, just doing this, just something that takes maybe 2 years from start to finish for construction, permitting, building, changing, could cover 18,000 homes worth of electricity. Yes?
Is this for future projects, or is this regarding all of Bonneville's installed transmission capacity?
Well, that's the neat thing about it, is you could do it on a brand new one, or you could put in all the data from an existing line and it will tell you where optimum points are. And then it's a simple matter of subtraction. So if I have them every 70 miles and the most optimum is 65, what am I losing by that extra 5 miles? This is basically just an Excel macros. It will tell you, this is how much you're losing by not having this at the most optimum point. And then the decision can be made there on whether this is something we need to retrofit or wait until the 40-year span and build from the beginning. Yes?
So I imagine that most of the rest, like the 10% that we're still losing, is due to like resistances in the line that we can't do anything about?
Well, I'm being conservative with the 5%. The 20% of losses that I stated are all ones that are from inductive and capacitive effects. So theoretically, we should be able to grab all of them, but ain't nothing work ideal in the real world. So I'm assuming that even if we only capture 25% of those 20% losses, 5% total, then this is what all my numbers are based on. Yes?
Is that based on what you expect to be economically viable to do, or is this more on a technical feasibility thing?
I went through just the lines that are in North Oregon and Southern Washington through BPA and calculated what the savings would be if this optimization was applied at all the lines out there that are supplying Portland. Because remember, we're shrinking down our view to make it easier to understand. So just in the Portland area, if we went through and we assigned a transposition at every single place where it says to put one, we would save at least 5%. Does it make sense to everyone? Any other questions?
Yeah. So if you go back to your cartoon with the 3 cents a line, almost when I referred to.
Yes.
So you talked about being in the physics of the materials that are there.
Yes.
And the properties of the materials. What else is going to influence the transposition optimization? Anything in the environment? Anything
Well, I mean, there are different things that I took into consideration. I took into, yes.
Can we just have her restate that question?
Oh, sure.
I don't think anyone heard her.
Yeah, absolutely. So I'm looking at your cartoon and recognizing that you described how all of the inputs are well understood, well known. And so my question is, what are some of the noise variables that can affect the optimized locations? Anything in the environment, anything in the weather pattern, anything in population centers that could be also impacting this? And is there a need to go and investigate that, or is this as clean as what you described?
Well, there are several things that can mess with the data effectively. If there was another line right next to this one, which is often how they do it, because you only have a certain amount of space that you can take up, those lines can mess with each other as well, and you can get additional inductive and capacitive effects. Elevation, air density can also affect how much corona you're getting, which is another way that these inductive and capacitive losses cause, I should say, physical demonstrations of loss. The different height, even the different grounds that are there below the towers, because clay has a very much different ground resistance than, say, granite does. So those are all the things that BPA takes into consideration. I used BPA standards because they're governmental, so they tend to be a little less profit-based. And I confirmed them with TVA, which is the government entity in the Midwest, to make sure that I was being consistent. So everything that they calculate for when normal building designs are decided, that's what I put into this. So there are other factors. I mean, obviously, if you had a big tower or something, a big skyscraper next to it, anything that can disrupt your magnetic or your electric fields is going to cause a variance in this, which is part of why I'm shooting for what I consider to be pretty much a guaranteed savings, is the 5%. Theoretically, all things perfect, we could get the full 20. I'm going to say we can get at least 5. Okay, so looking at this from just a dollar perspective, what we're expecting is in countries that are OECD groups, so have joined the Economic Energy Organization, we're looking at about $310 billion in potential profits, and that's just in increased electrical demand over the next 20-odd years. If we're to expand that to non-OECD countries, so places that don't normally have an electrical grid and aren't really on the global scale, that's a 1.7 trillion. And that's just in the potential savings for applying this 20% savings. And remember, there's 80% losses overseas. So if we expanded this to be, we save 50% of the losses, that's going to be even higher. Yes?
Okay, I think this will be my last question, but when you go about to do the transposing, do you have to lengthen the electrical lines? And if so, how do you go about doing that?
Well, the electrical lines are in a giant spool, like thread, and they attach one end, and then they just go until they run out, and then they splice a new line in. So having to lengthen it isn't specifically something that you need to be concerned with for transposition. It is something that goes into construction costs, that knowledge, because geometrically you are tilting them so they stay enough apart that you don't get arcing. So they are going to be slightly longer, but in the grand scheme of things, it's not something you have to calculate separately. You just run it from one tower to the point that you have on the second tower, set your sag, and move on.
So you guys are totally replacing the lines, not like reusing the lines that are already there?
Oh, if it's a retrofit, you reuse the lines that are there, because they'll still work. Okay, so as future engineers, who would you rather be? Would you rather be the person that has to sit at the desk day after day doing the calculations to figure out where you should put transposition? Or would you rather be able to just push a button on a computer and have it tell you where the most optimum place is so you can get on to, stuff that's shiny and cool? If you're a company and engineers are your most expensive resource, do you want to have your most expensive resource spend days doing this? Or do you want to have a software that they can spend 15 minutes doing?
For eliminating jobs?
Yeah.
There we go. Could you talk about that, maybe?
Well, honestly, in the power industry, they hired up back in the 60s and 70s, so currently they're about 25% undermanned. So I think that there are plenty of jobs there doing way more wicked cool stuff than transposition calculations. Okay, any other questions? Yes, Dr. Brissett.
Is the process of doing the transposition, or building the towers, et cetera, getting less expensive as we do more of them, as we get more best practices, or is it still going to be very much an individual design thing for every single time?
It's still going to be an individual design thing. The neat thing about this is that we have been doing it forever. We are masters at building electrical towers. So until we come up with a new way to transmit electricity, this is the way that it is. We are super, super good at doing this. We just don't know when to always do it. So that's where I stepped in. At this point, so my kids have told me technology runs everything. So we should have technology doing this and not a whole bunch of math. We should be doing cool stuff, figuring out fiber optic cables and new things to transmit more power. Not doing boring material calculations. Okay, so now that I have girded you all with my transposition knowledge, you can go out there and have the world bow to your efficiency power.